नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड नीट। आज मैं सॉलिड स्टेट का एक इम्पॉर्टेंट टॉपिक डिस्कस करने जा रहा हूं जिसका नाम है क्लोज पैकिंग इन 2D। यह टॉपिक इसलिए इम्पॉर्टेंट है क्योंकि हमें यदि किसी भी 3 डायमेंशनल क्लोज पैक स्ट्रक्चर को समझना है तो 2 डायमेंशनल क्लोजेस्ट पैक की ज़रूरत पड़ती है। इसके साथ ही JEE एडवांस 2003 की इस कॉन्सेप्ट पर बेस्ड प्रॉब्लम भी हम डिस्कस करेंगे। We have divided this video into two parts. In part 1, we have discussed the square packing and hexagonal closed packing of 2 dimension. Let's go through the first part. If we want to make one dimensional closed pack crystal, it can be made with the help of taking one atom. So this is one atom, and we are repeating this atom again and again. We are placing another atom nearest to this atom, right? There is no gap between these two atoms, and if we repeat it again and again, we can say that we have formed the whole crystal, and it is closest pack of one dimension. And if we repeat this closest pack, like if I am saying that this layer is A layer, and if I repeat this layer just below A layer, we are putting another layer which is of the same type. So this type of packing in 2 dimension is known as a square packing. So we have to understand that why we are saying that this packing is a square packing. We have to cover this whole area of 2 dimension, and if we join the center of these circles, on joining the center of these circles we are getting a square. So if I repeat again, we are getting another square, right? So this whole space can be occupied by repeating this square again and again. There is no gap in between. So we'll say that a square will act like an unit cell. Unit cell is a pattern which on repeating again and again will occupy the whole space. So we'll say that a square packing, square is a unit cell. Now in this unit cell you can see here that this whole crystal is made up of square unit cells. We are repeating it again and again, and we are forming the whole 2-dimensional crystal. So if we want to calculate what is the packing fraction of this square packing, so this is the square, and the blue color area is the area occupied by the atoms in this square. So if we write that what is the packing fraction, we can define packing fraction is area occupied upon total area. So area occupied, there are 4 circles in this square, but each circle, only 1/4 of the circle is present in this square. So we can say that area of a circle is pi r square divided by 4. So this is the total area occupied by these circles in the square upon area of the square. So area of the square, if you see that the edge length of the square is equal to 2 times of radius of atom or radius of circle. So if we put here, we can write that area of square is equal to a square, which is 2r whole square, and if we further simplify, we are getting pi by 4. So pi is 3.14. If I use calculator to calculate this value, 3.14 divided by 4, we are getting 0.785. So we can say that 78.5% of the area is occupied when we do square packing. So another type of closest pack in 2 dimension or close packing in 2 dimension we are discussing here. So we are taking the closest pack of 1 dimension, and we can name it. Suppose we are saying that this is A layer. So just below this layer we are placing another layer which is identical to A layer, but the position is different. Here the position of B layer is in the gap between the A layer, right? So since positions are different, that's why their naming is different. Again, the third layer is symmetrical in position to A layer, so that's why we are saying A layer. And again the fourth layer is exactly like B layer. So this is AB type of packing. So this is known as hexagonal packing. Why it is known as hexagonal packing? We can see here that this whole 2-dimensional area can be occupied by using these hexagons, right? So if you repeat these hexagons again and again, there is no gap between these hexagons. We can occupy the whole area. So hexagon is a pattern which on repeating again and again we can occupy the whole space. So now for this hexagon we are saying that the unit cell of hexagonal packing is a hexagon. This hexagon is made up of or 6 equilateral triangles. So on repeating these equilateral triangles we can find out this big hexagon. So either we can find the packing fraction of this hexagonal crystal, two-dimensional crystal, by using this triangular unit cell, because if I repeat the triangle 6 times I am going to get this big hexagon, right. So either I can calculate the packing fraction by using this small triangle. So if I am writing with the help of triangle, that what is the packing fraction? So packing fraction is area occupied. So area occupied in this triangle, there are 3 circles, but the angle, because it is equilateral triangle, so angle is 60 degrees, so only 1/6 of the circle is occupied, right. So we can say there are 3 circles, but the area occupied in each circle is equal to pi r square divided by 6. So this is the area occupied by the atoms or circles divided by the total area of this equilateral triangle. So we know that what is the formula for area of equilateral triangle, that is equal to under root 3 by 4 a square, where a is equal to 2 times of r. So if we further simplify, here we can say that this is equal to r square, and r square in numerator and denominator will cancel out, and this 3 pi by 6 is pi by 2. So here I am writing in numerator it is pi by 2. In denominator if we simplify, it is coming, because this 4 and 4 will cancel out. So this is coming root 3. So if we simplify, we are getting that the packing fraction is equal to pi by 2 root 3. On further simplification, we can write with the help of calculator. If you simplify this by putting the value of pi and under root 3, on simplification we are getting this value is equal to 0.907. So we can say that 90.7% of the area is occupied in this hexagonal close packing. Now if we try to find out the same packing fraction with the help of this big hexagon, so we can say that this big hexagon is made up of 6 small equilateral triangle. So the total area occupied by these circles in this big hexagon is 6 times the area occupied in one triangle, equilateral triangle. So we have to multiply in numerator by 6, and in denominator also, in order to calculate the total area of hexagon, we have to multiply by 6. So those 6 and 6 will cancel out. So whenever we have to calculate the packing fraction, the best way to calculate the packing fraction of hexagonal crystal is take a equilateral triangle, make circles at the corners such that they are touching each other, and with the help of that we can find out the packing fraction. So now if we compare that in 2 dimension, if we want to make a close packing, there are 2 type of close packing we can do. One is square packing, where the packing fraction is 0.785, and the other packing is known as hexagonal packing, where the packing fraction is 0.907. So 90.7%. So we can say among these two, hexagonal packing is the closest packing in 2 dimension.